of my go-to jokes with the people there is, I'd say, I don't like needles, and they're like, oh, most people don't like needles. And I'm like, well, I teach statistics. And I would argue most people would rather have their blood drawn than learn statistics. So we all do things that, we chose our own weird paths in life. And so, yes, I am legit this happy to talk about CFA, which is where we're doing now. As soon as I can get the window over to the right screen. Come on, you can do it. Mr. Mouse is like, no. There we go. So this is what I posted earlier today. It is on the course website if you haven't grabbed it yet. I'm calling it Lecture 4A. The slide deck originally was like 85 slides, and it was so huge that every time I saved it, it took 10 minutes to save, and so I decided to cut it up. So this is where I am starting from, the world of confirmatory factor analysis. So first up, a comparison of exploratory factor analysis and confirmatory factor analysis in terms of the high points. And if you have not had coursework or not done exploratory factor analysis, don't worry, you don't need to. It's fine. But for those of you who have, I wanted to make the contrast explicit. So what gets analyzed is the first thing that might differ between these. In EFA, it's almost always a correlation matrix. And remember that items and indicators are synonyms. You will hear me switch back and forth because in this literature, they're often called indicators instead. So we are not paying attention to differences across items in their means and variances, which could very well matter, especially if we're interested in comparing factor analytic solutions across samples or occasions. In CFA, we do pay attention. So what we care about in CFA, confirmatory models, is the full covariance matrix and mean vector of the indicators. So differences in item means, differences in item variance are part of the story, and the covariances across the items are part of the story as well. We can still convert this into a correlation metric so we can look at things a little bit easier and compare across items on different scales, but the unit of analysis here, what we're coming back to, is covariance. And you will hear me say covariance matrix. That really more properly is variance covariance matrix, where the variances are on the diagonal and the off diagonal are the covariances. And the output that we will get has two different kinds of solutions in CFA. One talks about how the model recreates the covariance matrix. That's unstandardized or sort of the default. And then a standardized solution refers to how the model parameters recreate the correlation matrix instead. It's the same result, just on two different scales. It can be easier for some purposes to look at one versus the other. Another is rotation. In EFA, by default, all items load on all factors. So you can tell your software, here's my items. I want to see what it would look like if you said there were 2 factors, 3 factors, and 4 factors. Go. And it spits them all back at you. And you're like, well, I think maybe 3. But we need to do a rotation. And this is a concept that takes far too long to explain, so I'm not going to do it right here. But there are basically different ways of reconfiguring your solution to make it so that the factor definition is clearer. And you can choose between factors that are correlated, which is an oblique rotation, set of rotations, or uncorrelated, which is orthogonal. You can't tell it what the interpretation of the factors is supposed to be, whether it's a content factor related to the trait or a method factor related to how you asked about the trait, such as reverse coding or differences between raters or things. And I don't like any of this because my fundamental belief is that it's not your data's job to tell you what it measures. It's your job. I have never seen a case where somebody had a set of items that they cared about and no clue what they were supposed to be measuring. Everyone has a clue. You don't have to be right, but you got to have a clue. So it's our job in CFA to say what we think the data are measuring and then prove me wrong. So it's theory-driven. Any structure becomes a testable hypothesis. You specify how many factors and whether or not they're correlated or what pattern they're correlated in. You can specify which items load on. That means relate to the factor. The factor is the predictor. And it's usually phrased as a yes-no thing, but there are exceptions in like Bayes land, for instance. If there are additional relationships beyond the traits, such as it's called method variance, right? If I have items that are like, I asked the parent to write this about the kid, and then I gave the same measure to the kid's teacher, Probably the teacher responses are going to be correlated just because they came from that person and the parents are too. So regardless of what you're asking about, you'd want to build that into the model as an extra expected correlation. And I repeat, you don't need a clue. You just need a clue. You don't have to be right. Because once you figure out you're wrong, the best part of it comes, literally Misfit will tell you where you're wrong. Which inter-item correlations have not been successfully reproduced can guide you as to where your hypotheses are incorrect. And you can fix it. So you can revise your model, see if it fits better. That's also usually a significance test of some kind, and end up with something that hopefully fits better, that you would then collect more data to try to replicate. So it's confirmatory in the sense that we set up the model. It's exploratory in the sense that we can change our minds and fit a new model. This EFA, though, is completely exploratory. Everything loads on everything, and reasonable people would come to different opinions as to what the right answer is. That's my problem with it. How many factors and whether the model fits is not a thing. In EFA, if you use maximum likelihood estimation, it could be a thing, but most cases do not do that. They look at things like scree plots, interpretability, and arbitrary cutoffs as to standardize loadings of 0.3 or 0.4. In newer software, you can get standard errors, but that's, again, not frequent. We'll have actual model fit inference. So we'll have 8,000 measures of model fit and diagnostics for it. We will have estimates, standard errors, and hypothesis tests for every single model parameter, including linear combinations thereof, and we can test changes to the model as to whether taking things away makes it worse and adding things makes it better. So we have control of all of that. Factor scores should never be used from an exploratory factor analysis. They're indeterminate. If you choose a different rotation, you would get a different set of factor scores, sometimes uncorrelated with the first sets of ones. In CFA, we can use factor scores, but the whole idea is that we don't want to. The latent trait can stay latent. We don't need to know what the factor score for any of our subjects is. We don't. We can still look at how this trait relates to this other trait in latent space. That's what SEM is for. So we're working our way up in terms of building measurement models to get a sense of whether our dimensionality hypothesis is supported, how reliably that trait is measured, and then the end game is to say, okay, now that I've got all these traits, how do they relate to each other in the ways that I want to know? So we're not going to need factor scores if we can do SEM. Now that being said, not everyone's going to be able to do SEM. If you'd have a relatively small sample, particularly given the number of items that you would have, then you may end up having to take shortcuts where you could output factor scores and then treat them as observed variables in a secondary analysis. That's not ideal, but there are strategies that are increasingly common, known as plausible values, where you would output multiple factor scores from a distribution and then rerun your analysis on each set of factor scores and combine the results. That way you're not pretending that your factor score is a perfectly known, reliable thing. There are large-scale testing organizations that do this. Is it NAEP? Is that the one I'm thinking of that has plausible values? Folks in ed? That's the one. Does PISA do that? Yeah. PISA does that too? Which one? TIMS? That's the one I was thinking of, yeah. So this is a common thing where rather than saying, no, I've got the person's factor score, you would take their factor score and treat it as a mean of a distribution, the standard error around that factor score as the standard deviation of their little distribution, and then you pull draws from it. So you're not assuming that it's perfect. You're treating it with error that it has. So that'll be like the last half of the last lecture. We'll talk about that a little bit, and I have some resources for folks if they want to do that. Okay, that was a quick coverage. I will remind you that more information about EFA and component analysis is in the Lecture 2 materials that I posted in ICON, if you really want to know. But I don't think you do. So here we are. Welcome to CFA. In CFA, we predict item responses. We don't add things together. So what makes this challenging is not the concepts. CFA is a linear regression model. The latent trait is your factor. The item response is your outcome. The latent trait predictor, Y, is your outcome. That's it. If you know that, you're good. What makes this hard is the notation. There's a whole lot of Greek. So my approach to this, and I've changed the notation somewhat since previous years to be a little bit stricter, I try to eliminate working memory load whenever I possibly can. So I make deliberate choices to use easier notation when it's possible. Letters you already know and symbols you already know. So this is the classic CFA model here, where mu is an intercept, lambda is a loading, F is a factor score, and E is error. And this is a model that describes multiple items and people at the same time, and that's why we have the subscript patterns that we have. So in this class, I is for item, S is for subject. I also could have done like P for person, but P is going to be for something else. So you run out of letters. That's the problem. So each item gets its own intercept. Each item gets its own factor loading. Each person, each subject, gets its own factor score. They're standing on the latent trait you're trying to measure with these items. And each item has a separate error for each subject. So IS. And in your textbook, the Brown CFA book, the chapters for which are in icon, he uses what I call, this is squiggle 2, as opposed to squiggle 1. Other people might call it psi. And he uses X for the outcomes, which is backwards because X are predictors and Y's are outcomes. So I switched these two things. F stands for factor. How's that? When you get frustrated with this, F might stand for other things as well, but right now it's just F for factor. I also only pick symbols that I can reliably write on a chalkboard. And squiggle 2 is not within my capabilities. I can't do that one. So if we break this down into the linear regression that it is, you will find that you already know how to interpret the terms. Yes, sir?
So the top equation is predicting a single item response for a single participant?
Yes, we're right. We wrote one equation for all the items sort of stacked together. Yep. And so things that have an I vary across the items. Things that have an S vary across the people, the subjects. And things that have both vary across both. I have equations that break it down per item coming, but this is sort of the cleanest representation to start with. So this looks a whole lot like linear regression. So if I wrote a one outcome linear regression model, so y for each subject is a function of some fixed intercept plus a fixed slope for x as a predictor and some residual e. If I added it for multiple outcomes at the same time with the I subscript we get to here, so then the translation from there is relatively straightforward. Beta 0 is an intercept. It's now going to be called mu, but it's still the same concept. It's the expected outcome when the predictors are 0. In this context, it's the expected item response, so y hat, you can think of it, when f is 0. Turns out, in most of the models you'll see, we're going to set it so that f has a mean of 0 for this reason. Beta 1 is a slope. It is going to be notated by lambda, but it is still a slope. Slope is the change in y for a 1 unit change in x, right? That's what it's always going to be. So contextually then, change in y, the item response, for a 1 unit change, or difference as I say here, in the factor. And I say difference because this is not a longitudinal result. No, people aren't changing into each other. They're just different. In most of the models that you will see, the factor score is measured such that 1 is the standard deviation for this reason. So then the slope is the change in the item response per standard deviation difference of the factor. E stands for error. Synonym of residual is the same thing it usually means. How far off are you? What's the difference between what your model says, the predicted item response, what the data say, the actual item response? I usually use the term residual for this when I teach other classes. In this class, I am going to try and say error instead. Because Residual has another meaning in this context of discrepancy between matrices. That's going to be our index of fit. So to try and avoid confusing you, I'm going to say error for this and then residual for that other idea. Okay, I see folks writing, thinking. Any of that you want to hear again or have me clarify? Okay, so then what do these terms mean? Item discrimination before was our item total correlation, right? Now it's lambda. It is the slope relating the item to the trait. We have a parameter that directly says how discriminating this is. And we want that slope to be as large as possible. These models are always phrased, by the way, so the slope is positive. So if you have reverse coded items, people typically would change them so that they're oriented in the same way as the others to begin with. That way your trait doesn't get confused. You can end up with multiple modes of your solution otherwise if the model doesn't know which way is up. The loadings themselves, though, are scale specific. So if I told you the slope is 0.5, you'd be like, is that good? You'd have to know what the scale of the response is to answer that question. So to make it easier to talk about discrimination in a way that is readily interpretable, scale-free, we will look at standardized factor loadings, which are directly equivalent to the idea of standardized slopes in regression. Same premise. Then, it's not a regression slope, it's a correlation. The other parameter is difficulty still, but now we have an explicit way of representing that. That's my intercept. However, this is not difficulty, this is easiness. Because items that have higher expected responses are easier. Easier to endorse, easier to get right, easier to agree with. The other thing I note about this is that the item mean is sample dependent, in that if we have a high mean, you don't know if you have smart people or it was an easy question. Now that we've separated out trait as a separate thing in our model, which is F, the intercept is the conditional item mean for somebody with a factor score of 0. So then it doesn't matter really what sample you took this from. Anybody at that level of the trait, this is their expected response. So it breaks the tie between the items and the people in the same way that happens in IRT. This is the same idea, just without the link function. However, your textbook and many others don't deal with intercepts at all. Like you'll see CFA equations in which they're not even there, and they'll say, oh, we just mean centered all the items. Bye-bye, no more intercepts. I don't like that. But the reason they can do that is that intercepts really don't matter in CFA, and here's why. This is a linear regression model. The relationship between the trait as the predictor, on the bottom here, x-axis, and the item response, linear means that the item is equally discriminating no matter where you are on the trait. So a good item is good if it has a strong slope. It doesn't matter where the intercept for the expected outcome at 0 is. Likewise, if an item has a low slope or a 0 slope, then it's a bad item and it's bad for everybody. So where this line happens to cross 0 is irrelevant to discriminating which items are good and which items are not so good. However, we're going to keep them in. They're going to be with us all semester for a couple of reasons. Number one, eventually, we're going to be testing factor mean differences, in which we need the intercepts to be able to do that. We can look at questions of invariance and potentially change over time. And because it's going to be a direct parameter in the IRT and IFA models, so let's just keep it in. So we'll keep both, but nobody really pays attention to item intercepts in CFA. All right, here's a fun picture. You're like, what? Do you have any idea how long these pictures take to draw? But I finally figured out how to make a decent curved arrow in PowerPoint after doing this for 20 years. It took me a half hour to make one, and once I got it right, I just pasted it in all the slides. I'm like, I'm not going to try to redo this, so I'm very excited for this new development. But this is a diagramming system that is supposed to describe the factor analytic model. This is an example that has 6 items and 2 factors. And the entire world has agreed upon a set of drawing conventions to do this, with very little variation. So I want to tell you what they are. Things that are imaginary are in circles. Things that are real are in boxes. By imaginary, I mean latent. So this has the box here, Y1, which varies over subjects, Y2, 3, up to 6. These are columns in your data set, usually in wide data format where it's 1 row per subject, usually. The latent traits are in the blue circles up here. I've named them F1 and F2. Very creative. They get an S subscript because they vary over people. Each of these item responses varies over people. The red line from the trait to the outcome, that's my loading. That's my regression slope. Just like in path analysis, if you've seen path diagrams from predictor to outcome, same direction. The arrow direction matters, okay? So you've seen those memes like, tell me you're something without telling me you're something. You've seen those before? Yes, you know what I'm talking about. Mine would be, if you get the arrow wrong, be like, tell me you don't know CFA without telling me you don't know CFA. The arrows are essential. They go from the trait to the box in these reflective measurement models. If you put it the other way, that is a very different model called a formative measurement model, and we'll talk about those later. So from the trait to the outcome. I've numbered these such that the first subscript is which item, the second subscript is which trait. So this is item 1 loading on trait 1, item 2 loading on trait 1. Over here, item 4 loads on trait 2, and so forth. The fact that there are no red lines going from F1 to 4, 5, and 6, and no red lines going from F2 to 1, 2, and 3, means I am saying these 3 items only measure trait 1, and these 3 items only measure trait 2. That's an assumption. It's testable. These 2 traits get to be related to each other through a covariance. So it's not like I'm saying that item 1 has nothing to do with item 6. The rules of tracing, which we'll get through as we get into this here, but just to foreshadow that, you can trace along the lines to figure out the model implied relationship to any of these boxes. So this model says that the only reason why Y1 and Y6 are related is because of the traits that they measure being related. Whereas Y1 and Y2 would be expected to have a direct association because they measure the same thing. Okay, with me so far? Now, my curved arrow here, that indicates a variance. I've labeled it with the variance symbol. So this is an example of me trying to reduce your working memory load. Everybody knows what sigma squared is, right? They've drilled that into you. That means variance. So I put a subscript for what it's the variance of to make it easy. This is one way of showing that something has a variance. It's the most compact way. The other is down here by making an actual separate circle for the residuals. So I could have made a curvy arrow on each of these boxes. Alternatively, I am showing E as a separate component that is needed to fill in what is left after the factor predicts this item. So here's my error, and it has a path of 1. So each of these E's is going to have an estimated variance as well, and I'm going to call that sigma squared E for error variance, like we usually do. So each item usually gets a separately estimated error variance. Each item usually gets a separately estimated slope or factor loading. Then we get to the stupid triangle. I hate the stupid triangle. It just clutters up the diagram. But what this is trying to build in the intercepts and means into the pictures. So if you write out, thank you, Vladimir, if you write out a regression equation in matrix form, you've got your X's, your design matrix, you've got your betas in the matrix next door, and to make it work, what has to be in the first column to go with the intercept? Like what variable multiplies your intercept?
1.
A column of 1s usually, right? That's what this is supposed to be. And they pick triangle because it's not a variable like a box, and it's not imaginary like a circle, so they just went with triangle, I guess. And I don't know who originated this, but that's what triangle is. It's basically making it so that you can stick the means and intercepts into your picture. So then we have from the triangle to the box, each of the items gets a separate intercept on both sides here, and then each of the factors gets its own mean in this case. And if the factor were to be predicted, these would become intercepts as well. So right now, the factors are the x's, the item responses are the y's. So down here, I have a summary as to what the actual parameters are. For the measurement model refers to how the items relate to their trait. So each item gets a factor loading and an intercept, but E is not an item thing. E is the idea that the predicted response is going to be off a little bit for each person. So what E represents is the idea that we're going to have an estimated error variance across subjects for that item. So there's a little bit of an asymmetry here. E is not a parameter, it's variances. Same thing with the structural model. That term means factor stuff, how the factors relate to each other and are distributed. So each factor is going to get its own mean, and I'm using kappa for that. You can have a covariance between factors, and I'm using sigma for covariance. And then F is the factor score for each person that varies across subjects. And so the variance of the F is what the model parameter is. So E is the idea of a variance, F is the idea of a variance in these things. Okay. Ta-da! And as a foreshadowing up here, I can't estimate every single thing in this picture. So some of this is going to have to be nailed down into known values for the rest of the parameters to be solved around it. That's called model identification, and that's like 20 slides from now. Maybe not, maybe 10 slides from now. We'll get there. Okay, 143. Questions? Comments? Are we excited? Thanks for pretending. I appreciate the enthusiasm. Yeah. All right then. If no one wants to talk to me or ask questions, then we can be done a whole minute early. Thanks for being here. Let me know if you need anything, and I will see you Thursday. Bye for now. Bye, Zoomers.